some partial results concerning the type of changes that could happen if the evolution ceased to be unitary. It's not working? So we saw from the analysis using purifacing that we modeled in terms of the Blarian master equation, that not only there were changes, there were dramatic changes in the sense that we were back to being standard quantum limited, which was not the plan. An important thing to notice is that the result we were using, imported from classical statistics, has a generalization in the quantum domain in terms of the quantum Roundabout. So now the issue is that not only do we have the problem of building a suitable estimator, but an additional degree of freedom is that we have now to perform optimization with respect to all the possible generalized measurements that you can have. My pointer is big. No, it's alive. Okay. One thing to remember, and that I mentioned before, is that in the moment that the time evolution is open, then we will have to determine an optimal interrogation time that is n-dependent in order to obtain the maximum possible value of Fisher information. Back to here, I think we're stopping here. Okay. So things we need to remember. In the classical setup, we had an additivity property for the classical Fisher information. So then this parameter here in the denominator has the meaning of really number of independent repetitions yielding to whatever likelihood we have here. In the case of the Roundabout bound, for the quantum setting where states are specified by a certain density matrix, then the Fisher information in principle can be defined as the trace of our state times an object that is an emission operator, so that in principle we do have a closed form for the optimal resolution that can be shown that should be even reachable in the limit of an infinitely large number of repetitions, and for an optimal measurement that corresponds to projecting onto the eigenstates of this final operator. So let's say that from a very formal point of view, we do have an answer to what is the optimal resolution in the quantum setup. The problem is that we face in general the issue of having to diagonalize an operator that will be highly inconvenient in the moment that the number of particles grows. So write it down exactly what is going to happen benefited a lot from techniques that were developed in the quantum information setup with the aim of characterizing quantum channels. And the trick is to move from mixed states to purifications and from states to channels. And so particularly relevant for what we're going to say in particular are the techniques developed by Asian collaborators in Brazil, and also work done in Poland and here by Rafael and Madeline. Okay, so what is the main idea? In the case of pure states, the quantum Fisher information can be written well in a form where I can avoid this diagonalization of the symmetric derivative. So the idea is I will try to find a way to characterize the quantum fission information that avoids that diagonalization, even if I have to pay the price that maybe the bound that I derive cannot be saturated. So let's see how far I can go with that ideas. Okay, so then if I call rho omega the result of my channel acting on whatever initial preparation I have, I will define the fission information for the channel as the maximum for all possible fission informations of pure input states. It's important to take into account that the fission information is a complex function. So it's sufficient that we maximize over pure states. Right, so now this is a whole story in its own. So my recommendation, if you want to go into details, is that you have a look at this. It's a rather long paper in the Journal of Physics by Janek Kolovinsky, which I believe was here visiting Gerardo. Yeah. Okay, so then maybe you already know some things about this procedure, and the other is Rafa that I mentioned a couple of times. Okay, the point is that there is a hierarchy of procedures that will allow me to set an upper bound for the fission information. And the main point is to use a theorem that I believe that Sabrina introduced that allows you, Spin-Weinstein theory, to be able to build up a purification in terms of having a pure state that now includes the environment, such that existing an environment will evolve unitarily by means of possible additional rotations on the environment. I will have a way to at least formally write down all the possible Krauss decomposition of the map that characterize the system evolution along. You can say, maybe you've moved from one very difficult task to another difficult task, and indeed, the issue of finding what would be the optimal Krauss decomposition, maximizing the fission information of the channel, is difficult. But it can be formulated in a way that can be solved by semi-definite programming. So this is actually the result that allowed to make progress. So using this type of techniques, it was possible to solve the big question mark that I left open in the previous lecture and prove that the result we obtain is indeed general. So in the presence of a pure dephasing channel, then indeed is the case that the resolution becomes standard quantum limited. Madeline and Rafael and the guy in the middle, is Janek Kolovinsky. So they went beyond and analyzed other types of noise. So besides dephasing, they consider depolarization channel and spontaneous emission, and then confirmed that indeed, in this case, asymptotically, the limit that you will get is that the efficiency of your procedure is bounded again as 1 to square root of n. I like a lot this picture because I think clarifies very much what is the scope of the analysis we are doing. Because whenever I talk about these things, especially if there are experimentalists in the audience, they tell me, but Dave Weinland made experiments with 2 or 3 ions, and he was achieving the Heisenberg limit. Okay, I think here you can see, and these are taken from this work and adapted here a little bit. You see, it's plotted the resolution as a function of the number of particles. You have the standard scaling in yellow, the standard quantum limit, 1 over square root of n for the resolution, versus the fundamental Heisenberg scaling in blue. So you see that in the moment that you start to move into the domain of not an infinity, but sufficiently large, you see that then the achievable precision that you get, and you see what is the analytical bound predicted with the analysis of the quantum Cramer-Rao bound, start to become close and close, and then the larger m becomes, there you hit standard scaling. If you decide to operate in this domain, then you see what is the meaning of being Heisenberg limited. You are still here, you have still not departed from this canonical bound. Okay? So then it's important that you remember this picture when you discuss whether or not in the presence of noise you have one type of resolution or another. Okay? The thing, emphasize once again, is that the same starts to grow, down you go, and there you will be Heisenberg limited for M10 Now, there was nothing fundamental in the techniques that prevented the application to time evolutions that were beyond the semigroup. I think simply in these previous examples, and Madeline is here and confirm, I think you applied it to semigroup times evolution because were the ones that have been analyzed before. But in principle, and we will use it later, this type of techniques allows us to go beyond. And from the lectures of Sabrina, now I think you have a more precise understanding on how to talk about Markovianity or non-Markovianity in a more quantitative way. For many years, and I think if you now poll most physicists, there is this intrinsic association in your head that Markovianity means living blood. Okay? This is a little bit restricted in the sense that you can also have Markovian evolutions that are not in linear form. So we're going to see that, in fact, whether or not you can model the dynamics in terms of an Imblavian type of evolution is very relevant from the point of view of the asymptotic resolution that you can achieve. So then the rest of the talk is going to be devoted to show that if the evolution, the open system evolution, is ruled by a map such that it does not obey the semigroup composition law, then we have a new fundamental bound for the resolution. We will not be able to achieve Heisenberg resolution, but we will get liberated from this nasty coming back to standard quantum limit. Okay, so again, I follow a historic approach and tell you how we got those results. So if we are analyzing purity phasing, you can in fact write down an exact model, have an independent boson model, normally called in the literature, where we model the whole universe as our qubit coupled linearly to a path of harmonic oscillators via a sigma set operator. In principle, we can work out what is the form of the decoherence function. And for very short times, or sufficiently short times, or model-dependent times, we can see what we obtain in the case that we approximate the decoherence function just as increasingly linearly with t. Take into account that normally you are used here now to exploring what is the behavior of different types of spectral densities you may have, but independently of those, there will always be a t sufficiently short for which that approximation should be okay. And then you can start to see why it's going to be relevant that the dynamics can or cannot be modeled by a semigroup. Because in the case of a semigroup dynamics, I will have a constant value for the dephasing rate, while in the time-dependent case that emerges from my exact model, here was a little bit exaggerated, but you will see that there will be a time domain, essentially when the system is really exploring what sort of frequencies are around, where t varies and will asymptotically approach the constant value. Okay, so this was results that we obtained in 2012, and there is also work in the group of Salmon Benjamin that did similar things in the context of magnetometry, showing that in this case, essentially, intuitively, you can explain it thinking that if you are able to interrogate the system in this type of timescales, effectively what you're being is subject to a reduced level of noise as compared with the one you have in the semigroup evolution. So then we can show doing the same calculations as before. So computing in a Ramsey setup with the classical vision information, what would be the resolution? The first thing we notice is that the new optimal interrogation time for the GAZ states with respect to the one of interrogating optimally product states scales now as 1 over square root of n. Remember that before I have to time the single shot experiments as 1 over n compared with the product ones. And what we obtain is that GAZ states, if I can perform experiments with this type of timescales, have a resolution that is not Heisenberg limited, but you see that now I'm not back to standard quantum limit. So it seems that if the evolution is not a semigroup one, then things are changing. But again, we are in a situation where even the form will provide the result, we don't know how general it is. Yeah? So then we have complete metrological equivalence between GAZ and product states in the case of a semigroup. We have this prediction for Heisenberg limited resolution, and now we encounter that if the time evolution is still rephasing the dynamics, but I have now time-dependent coefficients, then I seem to be able to go here. And having scaling that one may suspect that it should be universal, given that it emerges from the assumption that the whole system plus environment evolution is universal, so it is unitary. But nevertheless, one thinks that intuition, some partial proofs, and the other is show that indeed we can derive a new fundamental limit value in this case. And then this is the last thing we're going to discuss. In fact, Cassia, she's in Nottingham, showed that the result we obtain for pure dephasing is indeed general. So she proved it using the techniques of Erschner and company. And now we are going to try to go beyond relaxing that is pure dephasing only and consider the problem of the optimal resolution when the time evolution is phase covariant. So by that, what I mean is that the noise commutes with the action of the unitary time evolution. So if you do a qubit representation, then we can have the possibility to contract the Bloch sphere both along the z-axis and also in the equatorial direction, in the equatorial plane, even the possibility to displace it, and you may, if you want, have an additional rotation, so that this phi will be something random plus the actual precession by omega t. phase covariance, okay, it will allow us to derive analytically some results, but take into account that it is also from the fundamental point of view the type of noise we want to know how much damage is doing. If you are lucky and in your particular experimental realization all the noise is transferred to time evolution, then you can keep Heisenberg resolution. But the point is that even in those cases where you could perform forms of error correction, in the moment that you have a residual amount of noise that is phase covariant, then you are lost again. So then it's fundamental to know what is most damaging type of noise. Okay? In principle, we can write down what is the form of the map for this type of phase covariant evolutions, and what is also, for the quantum opticians in the audience, what is nice is that we can also write down what is the associated master equation. Then you see that in a phase covariant evolution, we can account for time-dependent dephasing, but we can also have the possibility of meet and absorb, and may have some additional lamp sheets in the internal energy. Relevant is that in order the evolution to be completely positive and trace preserving, we have some constraints that the parameters characterizing the noise have to obey. So if you remember what you've learned with Sabrina, this type of time evolution, which looks Lindbladian from the point of view of the form of the dissipator, take into account that here I've not imposed any restriction on the time dependence of the parameters. So in principle, this could describe a Markovian or a non-Markovian time evolution. I will remind you of the definitions in a second. Okay, so just to emphasize again, the association Lindblad-Markov can be naturally extended to be more quantitative. Take into account that the reason for that association is that one is used to derive master equations with an underlying microscopic model, which is fine, right? But then you're always relying on, to a certain point, hand-waving arguments that allow you to separate time scales in the time evolution of the system and of the environment. So from the mathematical point of view, it would be nice to also be able to characterize the presence of the absence of memory effects in more neutral terms, without having to explicitly refer to microscopic considerations. So this was the motivation in these works a few years ago to try to quantify, without reference to physics, if you want, what Markovianity means. So one possibility is to define Markovianity in terms of the divisibility properties of the time evolution. So given times, initial time, some intermediate time, and some final times, we will say that the evolution is Markovian if the map that connects the intermediate with the final time is also CP. So obviously, if your map obeys a semi-loop evolution, it would also be divisible, right? But there is also the possibility to have, like the master equation we have here, is also the possibility to have a Markovian time evolution in this sense, if these coefficients will always be positive at any time. If they aren't, then we say that the dynamics is not divisible and the time evolution is non-Markovian. This can be then linked to more physical intuition concerning backflow of information from the environment into the system, as I'm sure Sabrina told you. What would be then the idea to link these properties with a meteorological scenario? Well, very naively perhaps, one can think that if there is memory in the time evolution, and in particular if there is some sort of backflow of information, this may also involve the parameter I'm trying to estimate. So then it's not completely out of the question to think that memory effects in the protocol may be advantageous for metrology. So what we're going to prove is that, in fact, from the point of view of deriving asymptotic meteorological bounds, that's not the case. So really what is going to matter is what happens in the very, very initial part of the evolution. So the crucial property to no longer be constrained to standard quantum limited methodology is in fact not to obey the semigroup law. So in between standard quantum limited and non-standard quantum limited resolution is Lindblad, not Markovianity and non-Markovianity. Okay, so this would be, in more precise terms, what we have to show. And is that in the moment that we don't impose the semigroup property, it emerges a new fundamental scaling between these two extremes, where we will have that asymptotically the resolution is probably governed, when in fact, by the short time expansions of the parameter that intervenes in the contraction in the orthogonal direction to the one that determines the time evolution. And this, the way to prove this, which is a long proof, maybe normally once there is a long proof, maybe there is another shorter way to do it. But that's, again, another exploitation of the characterization of an upper bound for the Fisher information in terms of channel extensions. And this was done mainly by Andreas Nierlen and Jan Kolodinski, the Berkeley part. Okay. In relation with the memory effects and this intuition that one may have a benefit from possible information backflow, in fact, what we call the Zeno bound, simply because it's governed by the short time evolution, is that you need to impose the condition that one of the noise parameters is rigorously different from one. This is not a fundamental restriction, is that if this would actually be one, we would be in a situation where we have a time evolution where periodically is noiseless. But you can imagine that that, from the practical point of view, is very, very rare to happen. So if indeed you would have this sort of pathological evolution, if the most advantageous strategy would be waiting for their revival to happen, because they are effectively, the time evolution is noiseless, and then you do your metrology, which would be some sort of Heisenberg limited, okay? But let's say excluding that trivial situation, then we have that in general, in the moment that the evolution is open, the Heisenberg resolution is lost. But we are not back to the beginning. Okay, so this is just a very sketchy idea of the proof for those of you that may be interested. And the essential ingredients are three. On the one hand is to realize that the channel extension method allows you to in fact derive an upper bound for the feature information for the finite n case. And that the optimal decomposition of the channel can be done efficiently with semi-definite programming. They also provide you a seed for the cross operators that then you can use to obtain an analytical result. And the other important thing is that one can prove the convexity of the bound, which allows you to then apply the procedure separately for amplitude damping channel and unitary channels, where are easier to evaluate, and then derive what would be the bound for a general phase covariant channel. Okay? So essentially all boils down to prove that the optimal interrogation time is the one that as n increases goes to 0. So the optimal interrogation time happens in what we call the Zeno domain, despite I don't know whether the name has been a good idea, because this does not mean that you have to interrogate the system continuously like in the Zeno effect. Okay? So the reference to Zeno is simply the qualitative way to express that the larger is n, the shorter is the interrogation time. Okay, so just to confirm that on the one hand, okay, I'm avoiding many things, you could argue fine, but maybe indeed you can get some novel form of the scaling if you can interrogate in those short time scales. But what about the accessibility of the bound? Is indeed saturable? Indeed. One can prove that in GZ states you do saturate the bound, despite you only computed an upper bound for the feature information. And just to explore it a little bit more with a physical model, we explored whether in the case that the time evolution is governed by the Shabani-Vidar-Master equation, which is typically used to discriminate the behavior between Markovian and non-Markovian evolutions, is possible to saturate with GZ states the Zeno bound. Right. So somehow, having spent times exploring all the properties of non-Markovian time evolutions and so on, one would like to have situations where one can see that indeed having memory effects may be advantageous for something. So in this case, let me emphasize that the fact that the optimal interrogation time goes to 0 as n increases implies that from the point of view of setting an asymptotic bound, non-Markovianity and Markovianity doesn't matter. But this is a formal result. What I mean is that in practice, when you are operating A with a small number of particles and B with systems that maybe they cannot even be interrogated at the optimal time scale, Markovianity can be of practical advantage. Okay? So this is what I'm trying to illustrate in here. So I consider for simplicity the case of purity phasing and see what would be the typical behavior of the decoherence function. So this type of revivals are indicators of non-Markovianity, and the reason why you cannot associate an improvement or a lack of improvement to Markovianity itself is that you can always find a corresponding Markovian evolution that it will not have this colorful revival behavior, but from the point of view of the precision can always match the same lower bounds as you have with a non-Markovian, so with a Markovian map. Now, if in practice it happens that you can only well, it happens that indeed the evolution is not Markovian, so there is no way in trying to apply some equivalent from the meteorological point of view, Markovian evolution. Then you see that indeed can be the case that weighting is advantageous. But all then derives in a model-dependent, scenario-dependent situation. So it could be advantageous in practice, but then it will really depend now on the microscopic model, on the time scales that are accessible, etc., etc. So from the point of view of having a clear-cut result concerning bounds for noisy time evolutions, let me emphasize again that what matters is that evolution is not ruled by a semigroup. Subsequent Markovianity for the asymptotic bound is irrelevant. Okay, so I think I've probably emphasized the summary you have in there. So my main aim was maybe to clarify some things that by experience I know that people are a little bit confused, and I think it's important that you separate the low N from the large N, knowing that everything derived from the Kramer-Rao bound is meaningful asymptotically, right? And then when we consider noisy evolution and discuss Markovian versus non-Markovian, one has to be careful and take into account that what matters is not Markovianity. What matters is that evolution is not ruled by a semigroup. If it is, bad luck, standard resolution. If it isn't, then you can achieve a different form of scaling. How am I doing with the time? 10 minutes. There is a very related issue with metrology in the sense of parameter estimation, that is the determination of speed limits now for open quantum systems. So I put this as a bit of an open question. I thought for a moment after this result that we have a nice sort of closed loop relating metrology and speed limits and open systems, because again, if the dynamics is ruled by a semigroup, then I could derive the optimal interrogation time, or to be more precise, the ratio between optimal interrogation times for product states and maximal entangled states from a limit that we have for the time evolution, for the speed limits, which generalizes the old result of Van der Stam and Tam. So if I compute now, I forget about Kramer-Rao and everything, now I have a bound for what is the speed of evolution in the case of the having a map that I can model as a linear form. I can determine then from here what would be the optimal interrogation time. I do it for product and for GZ states, I see the ratio, and it coincides with the one we derived before. However, and this is Jan Kolodinsky and this is Andreas Milne, we tried, because in fact we had a result for the time evolution for a general CPT. So we tried to apply to a model. This is an old result from the group of Botkiewicz, for which we know what is the form of the Krauss operators. We determine from this bound what would be the optimal interrogation time, and in fact this would be a non-separable evolution. And then we were not able to recover the same optimal time for the non-Markovian case. So it would be pending to see whether I can get now a ratio of 1 over square root of n in the non-Markovian type of evolution. So the determination of speed limits and the determination of optimal bounds for parameter estimation, they are intimately related, but some additional care is needed to be able to exploit speed limits to obtain meteorological bounds. So everything I told you is collaborative work that started in '97, continued in the work with Alex Tina, Martin Plenio. We call it non-Markovian, which is not accurate, we could have said non-semigroup, and then the more recent results were done in collaboration with Warsaw. So this is the group in Ulm. It took us 5 years to finally have a group picture, and the guys in there are the ones in metrology. Okay? Andrea, Martin Plenio, and Jan Haas. Okay, and now let me show off a little bit, because this is the plan for the group to move in 2018 to a new facility. It's called the Center for Quantum Bioscience, currently under construction. So if people in the audience are looking for jobs, especially taking into account the recent developments, maybe you can consider the south of Germany. Okay, thanks for your attention. Everything clear? That's good. No, I think Casa didn't prove that. Casa would prove was that the bound that we got, right, you could obtain it via the maximization of the quantum fission information. Okay? So, in fact, if you want for pure phasing, showed that indeed is a fundamental bound. Okay? So then the subsequent work would prove is that it's not only fundamental for phasing, but actually for any phase-to-bounding dynamics. And that, moreover, can be saturated. And saturated what we said. Okay? Which, if you think about experiments in practice, for instance, in ion traps, we may argue that the noise is correlated. So for practical purposes, correlated phasing is relevant. But as it happens in deriving bounds in any direction, correlated error models, you know that they are tough, both spatial and so all the bounds we've discussed are valid in this cartoon I showed you, where the map is acting on every particle independently. Sorry, what can be the origin of a non-Markovian evolution?
Experimental, was the physical situation where an ant such that the sort of...
Right. Well, take into account the extreme Markovianity is a canonical limit that you will typically have in the presence of a very, very, very broadband environment. Okay? So in the moment that you have an environment that, for instance, is finite or even being very, very large, right, but has a correlation time that is still comparable to whatever time scale you may have in your system, then the typical assumptions you will do to derive what we call a Markovian master equation doesn't hold. So of course, with quantum optical systems, these type of conditions are very nicely obeyed, right? But in the moment that you enter in anything that does matter, that has matter relatively close, then you depart from Markovianity, okay? So you only have to see that the condition of exponential relaxation, that we would call it with this type of broadband environment, well, can be broken by many systems, and relevantly enough, in some of them is so large that it's not unfeasible to make interrogations of the system in that time scale. So I showed you one of the, I didn't emphasize what it was, but for instance, with realizations with nitrogen vacancies in diamonds, or type of spin systems, there we are collaborating with Fedor-Jelevsky to just academically show that you could be similarly interpret. So I would say that in reality, everything is non-Markovian, but in quantum optics, it's almost